So in this lesson, we're going to go over acids, bases, and salts. So let's get started. Acids generally go from the pH of 1 to 7, and the lower the number on the pH scale, the stronger the acid. Acids also conduct electricity, and as in Table J of your chemistry reference tables, they react with metals above hydrogen to produce a salt and hydrogen gas. They can also cause colors in acid-base indicators, and they're involved in double replacement reactions, also known as neutralization reactions, in which a salt and water are created. Acids also tend to taste sour, so if you ever feel the need to test this out, I'd suggest do not try hydrochloric acid, but maybe go with citric acid, as in oranges or any other type of citrus fruits.
Bases, as opposing to salts, have a pH range from 7 to 14. The higher that the number is, the more basic the solution is. It is also a great conductor of electricity. It can cause color changes in acid-base indicators depending on how strong of a base it is, and they are involved in double replacement reactions, which are also known as neutralization reactions, in which a salt and water are created. Also, if you were to ever taste a base, they taste bitter.
Salts are known as electrolytes, and generally we seem to think of salt as, table salt or, the salt that we use in cooking, but salts are just any ionic compound. So as you may remember, that's a metal and a nonmetal. So, even salts can be acidic, basic, or neutral depending on the strength of the acid or the base used in the formation. As in, if you had a neutralization reaction with a strong acid, the salt produced would most likely be acidic, and vice versa. If you were to use a strong base in your reaction, your salt would actually be considered basic. But if we were to use both a strong acid and a strong base, that would mean that the salt is neutral.
The pH scale measures the relative acidity of alkalinity of a solution. A pH value of 7 is neutral, and acids have a pH of below 7. The lower the number, the stronger the acid. Each decrease of a whole number of pH is tenfold increase in acid strength. An acid with a pH level of 3 is 10 times more acidic than the pH value of 4, and vice versa.
So there are two types of acid-base theories that we're going to be talking about. The first is Arrhenius acid-base theory, and the second will be the Bronsted-Lowry theory. So the Arrhenius acid-base theory was hypothesized by a Swedish scientist named Svante Arrhenius, who hypothesized that acids and bases are electrolytes, so therefore their properties are based off of their H plus and OH ions respectively, and they must produce these ions in solutions. So acids release H plus ions, hydrogen ions, which can attach to water, forming hydronium ions. Adding an acid to a solution increases the hydrogen ion concentration, and Table K has examples of these. If you notice, the acids in the acids that are given in that table all have a hydronium ion attached. And bases, on the other hand, release hydroxide ions, which become the only negative ion in an aqueous solution. So obviously adding a base to a solution increases the hydroxide ion concentration, and Table L has examples of these. Table L will have mostly strong bases that all have hydroxide ions attached to them. So if you ever need to remember for Arrhenius theory, you can always look back at these tables to double check.
The second theory is Bronsted-Lowry acid-base theory. In the Bronsted-Lowry acid-base theory, acids are the hydrogen donators and bases are the hydrogen acceptors. You can use the acronym BAD, B-A-A-D, not just one, to help you remember this in order to identify the acid-base conjugates.
So when you combine a strong acid and a strong base, a water and a salt is produced. So on the side here, we have a couple different examples, and the important thing is whenever you see these type of reactions, you should try and balance them just to make your life easier. So we can see in the first reaction there's not really much to balance. There's one hydrogen, there's two hydrogens on both sides. There's a nitrate ion, there's a sodium ion, and hydroxide, and obviously, you know, the water, we can see it as an HOH, as in a hydronium, I mean not hydronium, hydrogen ion and a hydroxide ion, as Miss Foley's probably gone over with you guys. And then we do have two more examples if you guys do want to look at neutralization reactions one more time before your Regents.
Titration is adding measured volumes of an acid and a base of known concentration to an acid or another base of unknown concentrations until neutralization occurs. There must be a 1-to-1 ratio of the hydrogen and hydroxide ions. In order to figure out the volume or concentration of either the acid or the base, the following equation is used. MAVA equals MBVB. Now, make sure that you are well aware of the number of moles of both the acid or the base, because if you don't, then it can mess up your answer.
So relating to titrations, you know, we have to use indicators to figure out the approximate pH range for different bases and acids. So generally, this is common knowledge that you need when performing a titration, and they're actually given to you on table M of your reference tables. So indicators are used to convey the range of the pH of the solution. It helps you compare the strength and acidity and basicity of the solution. When it comes to determining the color of the solution, refer to your table, and on the right, you know, we do have some examples. Methyl orange, approximate pH range is 3.2 to 4.4, and obviously the color range is red to yellow. And then we have, that's for like more acidic solutions, and then we have thymol blue for some more basic solutions, you know, that goes from 8.0 to 9.6 on the pH scale, and that has a color change from yellow to blue.
So now that we went over the material, let's go to the practice questions. Number 8, which two formulas represent Arrhenius acids? Now, remember that Arrhenius acids are the ones with the hydrogen ions. So A doesn't make sense because instead of hydrogen, you have hydroxide. Now B does have the hydrogens, so it's the correct answer.
It can't be C because, you know, there's not really any donating or accepting of hydrogen ions going on, and obviously D has no hydrogen or hydroxide ions to begin with. So B has to be the correct answer for 8. Obviously, the numbers on these questions are a little messed up, so kind of just ignore them. But number 7, as it's said on the slide. An Arrhenius base yields which ion as the only negative ion in an aqueous solution? This is, you know, straight up definition, and you guys should know this as D, the hydroxide ion.
Yay!
So over here we have number 5. It asks which compound is an Arrhenius acid. We have sulfuric acid, potassium chloride, sodium hydroxide, and ammonia. So automatically we can cross off B. There is no hydrogen or hydroxide ions involved. Hydrogen or hydroxide ions involved. So therefore the answer cannot be potassium chloride. So we're down to A, C, or D. D, as we know, ammonia is a weak base, so that cannot be the answer either. And if we go back to the original definition of an Arrhenius acid, it is when there is a hydrogen ion present. So therefore, your answer has to be A.
Continuing on to number 16, according to one acid-base theory, so it could be either or, a water molecule acts as an acid when the water molecule, so now they're talking about Bronsted-Lowry theory, and according to that, the acid has to act as a donator of the hydrogen ion. So this is also straight up definition, and the answer is, you guessed it, C.
This is another good example of where these acronyms do come in handy. If you had remembered bad, bases accept, acids donate. So acids donate is our answer here. So good luck on your test, guys. Just remember all the acronyms.
Continuing on with the questions. Number 10 asks, what is the pH of a solution that has a hydronium ion concentration of that's 100 times greater than a solution with a pH of 4? So now we're gonna, since it's hydronium, we're turning more acidic. So you know that the pH is gonna be lower. So it's not D and it's not A. Now, since it's 100 times and you know that pH levels are in increments of 10 times, you know that you're going to be changing two pH levels. So the answer is B.
And then we have number 9 here, which asks which ion is the only negative ion produced by an Arrhenius base in water. And as we all know, the answer to that should be C, given our definitions. So, yeah. So these last couple questions are based actually off of the Bronsted-Lowry theory. When we have questions that relate to the Bronsted-Lowry theory, we're going to write out our acronym BAD, bases accept, acids donate. So in these reactions, we're actually going to figure out which one is the acid and the base in the reactants, and then which one would be the conjugate acid and the conjugate base in these reactions. So we have here H2SO4 and the hydroxide ion, which reacts to give us HSO4 and H2O. So hydrogen, well, sulfuric acid here is actually losing a hydrogen, if you notice. So if it's losing a hydrogen, that means that it's actually giving away the hydrogen. It's donating. Therefore, this would be an acid. Oh, sorry. That was an ugly A. But this would be the acid, and then this would become the base, because bases accept. And if you look over our water here, we actually accept a hydrogen. So this would be the conjugate acid, and this would be the conjugate base. So at the end, we have H2SO4 as our acid, OH minus as our base. We have HSO4 minus as our conjugate base, and we have H2O as our conjugate acid.
Alright, well, since there's no space, I'm really not going to write it out. Oops. So in number 2, it's HSO4 plus H2O produces SO4 plus H3O. So the HSO4 is the one that's donating the hydrogen, so it is the acid. And the H2O is the one that's accepting the hydrogen, so it is the base. Now, if you go look on the other side, the H3O is the one that's donating its hydrogen, so it would be the conjugate acid. And the SO4, as a result, would be the conjugate base.
Moving on to number 3, we have a hydroxide ion plus a hydronium ion reacts to create 2 waters. So we thought it'd be easier if you saw the waters laid out next to each other side by side. But again, here we have hydroxide, which accepts hydrogen. So this has to be the base. And then obviously that would be its conjugate acid. And then we have H3O plus, which actually donates a hydrogen ion to create water. So this becomes the conjugate base. So as we can see over here, water acts as both a conjugate acid and a conjugate base. And when there's a substance that can act as either an acid or a base, depending on the reaction, we call those amphoteric substances.
So the final question, number 4, NH3 plus H2O produces NH4 plus OH. So in this one, you could see that the NH3 is accepting the hydrogen, so it is the base. And as a result, that's so bad. I apologize.
Oh my god. Okay, well, you guys had the notes on there.
We tried it.
But
let's just...
Yeah, that's our base, and then that will become our acid.
So this will be the conjugate acid, and then the conjugate base because of bad. Sorry, guys. But yeah, that's about it.
Sorry for all the little mishaps, but good luck on your test, guys. I'm sure.
This.
Yeah, you got
killed
this.
It. Woo!